Okay, so today we're going to start talking about plate tectonics. Our first step of that is continental drift. So our objectives for this PowerPoint are we want to be able to explain the different evidence for continental drift, we want to explain who Alfred Wegener was, and explain why Alfred Wegener's theory was rejected. Our vocabulary terms for this part of the unit are Pangea, continental drift, and Alfred Wegener. So Alfred Wegener was a German climatologist and Arctic explorer who suggested the concept of continental drift. So he studied mostly weather and not so much geology, but he was the first person to suggest the theory of continental drift, which was the idea that the continents moved around the Earth's surface. So Wegener thought that the continents were once all together in a supercontinent that he named Pangea. So over here we have what Pangea he thought might have looked like 225 million years ago. These would have been the continents that were together and how they were arranged. So like many people have noticed, the different continents look like jigsaw or puzzle pieces that fit together. So if you look, it definitely looks like South America and Africa were once together. So that was what many people once looked at and saw, but he was the first one to say that, hey, they were once together and that's why they look like puzzle pieces. Plate tectonics, which we'll study later, describes how these pieces of the Earth's surface move. Wegener's belief was a scientific hypothesis based on observation. Continental drift was not accepted by all scientists because there is no evidence to explain how the continents moved, and he wasn't a geologist. So since he was just a climatologist and studied different climates and weathers, many geologists didn't believe his theory, even though he had a lot of evidence to support it. But since he couldn't explain how he thought the continents were moving, nobody accepted his theory. So some of the evidence that he had were coal beds stretched across the eastern United States and the southern part of Europe. We had matching plant fossils that were found in South America, Africa, India, and Australia, and Antarctica, which you guys saw in your far-flung fossil expedition. Matching reptile fossils that were found in South America and Africa, and matching mammal fossils that were found in South America and Africa. Remember, these types of fossils wouldn't have been able to be separated by oceans since most of them were plants and freshwater mammals that wouldn't have been able to swim across the oceans. More fossil evidence in South America and Africa, found in rocks. They had matching mountain belts found from North America and the British Isles, Africa, and South America, and evidence of glaciers that were present in regions that now have warm and dry climates, which you guys saw in your far-flung fossil expedition. So we saw glacier evidence in regions that wouldn't have been able to support glaciers today. So these continents are now close to the equator, but back in the age of Pangea, 225 million years ago, they probably were closer to the South Pole, which would have been able to have a climate to support glaciers. So this is just a picture showing those different fossil evidence that we saw and how everything would have fit together, which you guys saw a lot of during your far-flung fossil expedition. This again is just a different map. You guys saw a lot of these different fossils during your expedition. So this is showing you how they were once together and how these fossils were, or animals, where they lived. This is again showing us the glacier evidence. So the top is showing us how these were once together based off the glacial evidence, and then the bottom is showing us where they are today. So these regions wouldn't have been able to support glacier evidence or glaciers today, but back 300 million years ago, they were much closer to the South Pole, which is why the glaciers would have been able to exist there. So the rejection of his hypothesis. So the main objection to Wegener's hypothesis was he could not describe a mechanism or a way capable of moving the continents. Wegener had a couple of theories. One was he proposed that the tidal influences of the moon was strong enough to give the continents a westward motion, which is not true, so that further rejected his hypothesis. And Wegener proposed that larger continents broke through oceanic crust much like icebreakers cut through the ice, which again was untrue. So because he couldn't explain how or the mechanism how they moved, his theory was rejected. So right now you're going to want to fill out your check for understandings and make sure all of your notes are complete for part 1 before you move on to part 2. Alright, so during part 2 we're going to talk about seafloor spreading. So our objectives for this portion of the notes are to explain who Harry Hess was, explain what drives seafloor spreading, and explain what a mid-ocean ridge is and what are their characteristics. So remember that we have evidence for plate boundaries. We have the different fossil evidence that are used for continental drift. So these are different fossils that we find spread out across different continents that are separated by oceans, even though these are freshwater or land mammal creatures who wouldn't have been able to swim across the ocean, suggesting that, again, all the continents were once together. So American geophysicist Harry Hess helped develop the theory of plate tectonics. These are just pictures of him. While he was an officer, Harry Hess helped map the ocean floor. So over here, this picture is just showing sonar, which is showing how they map the ocean floor. They would send a signal down, and then the signal would come back up, and depending on how long it took the signal to return back to the boat, they could figure out what the depth of the ocean was at that time, or at that place. Naval maps show undersea mountain chains that formed a continuous chain down the center of ocean floors, and he wondered if new ocean floors were being created at the mid-ocean ridges. So before Hess, most geologists believed that the ocean floor is flat, but with the use of sonar, they were able to map out the ocean floor and see that it wasn't flat, but there are many valleys and ridges throughout the ocean. So this is an example of a mid-ocean ridge, is what Harry Hess found. So as seafloor is made at the mid-ocean ridges, continents were pushed away. So he called this hypothesis seafloor spreading. The key was the discovery of the magnetic patterns and rocks on either side of the mid-ocean ridges. So here's what we were talking about. No, the ocean floor is not striped like a zebra, but what this is showing is that throughout time at the mid-ocean ridges, they had different iron minerals aligned towards the North Pole and the South Pole, and they were identical on each side. Matching magnetic patterns and the age of rocks of mid-ocean ridges provide stronger evidence of seafloor spreading. So what this diagram here is showing you is that at mid-ocean ridges, we have magma coming up. Okay, this is where the new rock is created, and so at the mid-ocean ridges, we are going to have our youngest rocks. As the young rocks are created, it's going to start to push the older rocks outward. And this is all symmetrical. So if I were to take samples of rocks from this side and this side, they would be of identical age. If I were to take rock samples over here and over here, they would also be of identical age. It's the symmetrical pattern at the mid-ocean ridges, with the youngest in the center and the oldest further from the center. So as you walk along the mid-ocean ridges, you're going to get older and older rocks. Scientists realize that large pieces of the Earth's surface move about like rafts on the river because of these mid-ocean ridges, and we called these raft lithospheric plates. Plate tectonics study these lithospheric plates, which we'll talk about later. So there are two types of lithospheric plates. We have oceanic plates and continental plates. So continental plates are mostly andesite and granite, and oceanic plates are mostly basalt, but they all, since they're coming from magma or lava, are going to be igneous type rocks. So convection cells in the lower mantle are what drive the lithospheric plates on the surface. So if you guys think about if you think about a lava lamp, when you get a lava lamp and you turn it on, all of the wax is at the bottom. So as the light at the bottom of the lava lamp starts to heat up the wax is going to rise to the top of the lava lamp because it is becoming less dense because it is heated. As it's away from the heat source, it's going to start to cool. When it cools, it's going to condense and fall back down to the heat source, and the whole cycle will repeat over and over again. That's what's happening over here. So we have the core, which is very hot. It's going to start to heat up molten material around the core. It's going to rise up and create mid-ocean ridges, and then eventually cool and fall back down. When the new rock is pushed up at the mid-ocean ridges, somewhere over here, it's going to be being pushed back down in subduction. So what I always say is, if you make it, you have to break it. So if new rock is being made somewhere, that means that old rock is being destroyed and the subduction zone somewhere else, because it's being forced into subduction. It's sinking back down. Heated lower mantle material rises towards the Earth's surface. So if we go back to this slide real quick. So this again is just showing you that the red arrows indicate hot, expanded, less dense, and more buoyant, so it's going to rise up to the mid-ocean ridges. And then the cool, contracted, denser is less buoyant, which is what's going to happen at subduction. It's going to sink back down. And eventually, this material will be heated and again appear at the mid-ocean ridges. So it's kind of a recycling process. And again, the sinking is called subduction, and it occurs because it's going to be cooled, dense rock falling back down. A single hot rising plume is called a mantle plume and can cause a volcanic eruption in the plate above it. If the eruption is strong and lasts long enough, then the volcanic eruption may form an island on the plate. After the island forms, the movement of the plate carries it away from the mantle plume, and this is how we can determine how quickly plates are moving. So we can measure the speed of the movement by measuring the chains of the island. So we can figure out how old is the rock at each island and figure out the distance it traveled from the plume to figure out how quickly these plates are moving, which is about 2 centimeters a year, or the rate at which your fingernails grow. So on your note packet you have this diagram. You're going to explain what's happening at each of these. So at B, we have a mid-ocean ridge. So describe what type of rock do we have there. Is it new or is it old rock? At A and C are what we call trenches and where subduction is occurring. So describe the type of rock that is there. Is it new or is it old rock? Is it buoyant or is it a dense rock? And once you finish, you should have something that looks like this labeled and all.